Okay, this lecture is going to be a little bit shorter, and you'll see why. We're going to look at linear approximation and orthobases. So as you recall, we've already looked at linear approximation, and we found that we could take some basis set and form this Gramian matrix. And over here, column A is what we were trying to find as the coefficients for our approximation vector. And all we had to do was invert our Gramian matrix, multiply that by our desired signal that's projected onto our basis, and we get the coefficients. So a nice straightforward way to do this. A lot of you may remember, and certainly I did for the first couple times, you have to keep reminding yourself that there's another way to do this. Actually, I misspeak. What I remember when approximating a signal with a basis is not what I just showed you. What I remember is this method that we're about to discuss. This method only works with an orthobasis. So assume we have a Hilbert space with a subspace T. Then, if some set of vectors v1 up to vn is a basis for T, then an x hat within T is going to be A1, B1, so on and so forth, up to AN, BN. And we found, where the vector A is equal to G inverse B as defined previously. Above. Okay. But here's the beauty, and that is if our same set here is an orthobasis, then G is going to be equal to the identity matrix. And therefore, our coefficients, A1 up to AN, are just equal to the projections, X onto V1 up to X onto Vn. Or in other words, that is a to the I, or a of I, is equal to x v of I. Now this is what a lot of people remember from linear algebra. And it's true, but it's only true if you have an orthobasis. And I hate to say this, but I have been known on quizzes later in the semester to give you some basis and ask you to find the coefficients. And the basis is not an orthobasis, but people tend to automatically kind of fall into this this much easier idea that all you have to do is project your vector onto the basis and you have your solution. That is only the case for an orthobasis. And a substantial number of students forget. But forewarned is forearmed, and I don't think you are all going to forget, because I've now told you. And I want you to remember that this is only for an orthobasis. Okay. It turns out one other thing that I wanted to bring up, and that is, even in the case where you have an infinite basis, we can still approximate a signal using orthobasis. And so this is one other thing. This becomes really not so much approximating as simply an orthobasis expansion. So suppose, for example, T is the space itself. So if T is the whole space S, as described above, a Hilbert space, then any point in S, the closest point in T will be the point itself. So given X in S, the closest point in T is the point itself. And so we have, it's basically the same thing, but we're going to call it something just slightly different. That is X, some vector X, I'll be careful with my vector notation right now, is equal to the sum over the entire basis So if it's an infinite dimensional space, this works as long as the sum of all the projections, the absolute sum of all the projections squared, is finite. Also works for infinite dimensional spaces, as long as, and this is the convergence that we talked about, say, with the Fourier transform way back in your grade school days. In which case, if that's true, then we can write that x is equal to sum minus infinity to infinity of x with v times vn for an orthobasis. So, that was a quick lecture because orthobasis expansions are pretty simple. Once we have an orthobasis, approximating a signal or a vector in that space becomes almost trivial. So, till next time, stay safe.